Swayam Prabha. Digital India. Educated India.
Welcome to the 32nd lecture in mechanics of materials. Till now we have been solving different boundary value problems after having looked at what stress and strain, force and displacement are and the equation that are connecting them. Okay. Now we have been analyzing the structures as though the constellation that we used holds throughout for the response of the material. Okay. That is not the case. The constellation holds only up to a particular limit. For example, the Hooke's law that we used holds only until the response of the material is elastic. Okay. So, you have to tell the limit up to which the constellation holds, or in other words, if the structure is, if the material is failing, you have to tell what is the stress beyond which the material will won't withstand the applied load. Okay. So, this is where the failure theories comes in. First we have to understand what we mean by failure. Failure means not crushing of concrete, not crushing of wood necessarily. Okay. What it means is the inability of the structure to serve its intended purpose. It can be that the displacement has exceeded a particular limit, causing the structure not to perform its intended task, as in the case of a Doppler antenna or your cell phone towers and things like that, where the geometry of the structure is more important than its ability to withstand the wind loads or the loads that are coming on the structure. Okay. Similarly, you know that all reinforced concrete structures there will be a crack in the tension side, which does not necessarily mean the structure has failed. Okay. We design it with the cracks so that it can still withstand the applied load. Okay. On the other hand, the same reinforced concrete structure, if you cracks in the water tank is not allowable, because water will seep in, will cause some chemical degradation of the concrete and the steel, which can corrode. Okay. So, in one scenario what is acceptable may not be unacceptable in some other scenario. So, you have to be clear on what you mean by failure. Now, for our lecture here, what we mean by failure is the limit of applicability of a constitutive relation. Okay. In particular, the limit of applicability of the Hooke's law. Okay. That is, we are assuming that the material responds elastically, that is, it regains its shape and it does not dissipate any mechanical energy. So, when will this assumption stop to hold is what we are interested in finding. Now, you can formulate failure theories using either a stress based approach or a strain based approach. There have been theories based on both stress and strain, but most popular theories are based on stress. There is a reason for this. The reason is the strain, or what is the observable strain, need not necessarily cause failure in a body. I will give you an example. Take an example of a freely expanding body due to temperature changes. You know that there is no thermal stresses or there is no stresses in the body because of a free expansion of a body due to rise in temperature. Okay. But there is a strain in the body. So, theories that are based on strain should in particular be based on the mechanical component of the strain and not on the total or the observed strain. For this reason, the failure theory is based on strain as a limitation. On the other hand, if the theory is based on stress, there is stress in the body, means if it exceeds a particular limit it is going to fail. Okay. So, the stress in the body will be induced only by mechanical strain. Even though the mechanical strain and mechanical stresses are related in a one-to-one manner, when the body is elastic or it undergoes an non-dissipative response. Okay. You can formulate both in terms of stress or strain, but it has to be the mechanical component of the strain that you have to get into the failure theory, which is difficult to estimate in a general scenario. So, most failure theories are based on stresses. There is another reason why you base your failure theories on stresses, because there are bodies which can be residually stressed. For example, in the last lecture we saw a composite cylinder, right. the same composite cylinder can be formed when you by a process called as a shrink fit process, wherein the inner steel pipe will have a outer diameter which is slightly greater than the copper steel pipe inner diameter. So, what you do is you cool the inner steel pipe so that its diameter reduces, you put it into the copper pipe, the outer pipe, and then you allow it to come back to its room temperature. Then what happens is basically there will be a interfacial stress developed because the steel pipe is trying to expand, which the copper pipe is trying to prevent. Okay. So, there will be in that case residual stresses, or even though there is no traction on the surface of the body, there will be locked in stresses which are called as residual stresses in the body. Many manufacturing process will result in the body having residual stresses. Okay. So, basically these residual stresses have to be accounted for in some manner, which you can do when a theory is based on failure theories, or the limiting boundary is defined in terms of stress rather than the strain. For these reasons, your failure theories will say that it is based on the stress. Okay. Now, what does these failure theories try to depict? There are 6 components of stresses, and you know that the 6 components of stresses, the value of those 6 components of stresses depends upon the coordinate system that you choose to study the particular problem. Does the failure of a body depend upon the coordinate system that you choose to study the problem? No. If I pull a chalk and if it breaks, the failure is not determined by the coordinate system I chose to represent it. It depends only on the stress state that the body is subjected to. So, basically you can't base your failure theories on the computed components of the stresses. It has to be independent of the coordinate system. Some quantity which is independent of the coordinate system has to be used to formulate the failure theories. Okay. So, it should be based either on the principal stresses or the principal invariance of the stress. So, what this failure theories essentially tells us is the region which is safe in the stress space demarcated by the surface from the unsafe region. So, if I were to consider a 3-dimensional space with the principal stresses sigma 1, sigma 2, sigma 3 as the coordinates of that space, then what this failure theories will give us is a surface in this 3-dimensional space, okay, which will demarcate the safe region from the unsafe region. If it is inside the surface, the point, the stress state is inside the surface, it is safe. If it is outside the surface, it is unsafe. If it is on the boundary of the surface, it is on the verge of failing or on the verge of losing its ability to model a given response. Okay. So, essentially what we are after is in formulating this failure surface or the yield surface of the or the limit of applicability of the constellation. Okay. So, from our discussions till now, it is clear that I want to find a function f as a function of sigma equal to 0, where this is a 6-dimensional space of the 6 components of stresses in general. Okay. Since it is a surface, it is a scalar valued tensor function. Okay. Now, for this scalar valued tensor function to be objective, meaning it should fail only when the stress state exceeds a particular limit and not depend upon the coordinate system used to study the problem. This has to depend upon in general the principal values of stress and the principal directions n1, n2 and n3, where sigma 1, sigma 2, sigma 3 are the principal or the eigen stresses and n1, n2, n3 are the principal or the eigen direction. Okay. So, this has to be the case. Now, if the body can fail in any plane, there is no preferred plane of failure of a body, then it will not depend upon the eigen directions. Such a material is called as an isotropic material. This will reduce if I assume isotropic material, that is no preferred failure plane, then the failure criteria will reduce to depending upon the principal values of the stresses sigma 1, sigma 2, sigma 3 equal to 0. Okay. Now, what happens when there is a preferred failure plane like in a wood wherein the fiber directions does not fail easily compared to the direction perpendicular to the fiber orientation of in the wood. Okay. Then it will depend upon n1, n2, n3, then it will depend upon n1, n2, n3 which are the principal directions. Okay. In particular there will be factors coming in like where m is the direction of the fiber, m dotted with n1 kind of quantities will come in the failure theory. Okay. We will not look into these in this course. Okay. We will look at only isotopic materials, which means depends only on the principal values of the stress. Since it is difficult to compute the principal values of stress, you know that you have to solve cubic equation to find the principal values of stress in general. What you do is you base it on the principal invariance instead. You base it on K1, K2, K3 the principal invariance of these stresses, where K1 is nothing but trace of sigma, K2 is nothing but 1 half trace sigma squared minus trace of sigma square, and K3 is nothing but determinant of sigma. These are the principal invariance of stress. Okay. These are the principal invariance of the stress tensor. Okay. So, basically you based on K1, K2 or K3.